Everyone. So today we'll be solving the problem number tip for today, and this problem is 239, and it is sliding window maximum. The difficulty of this problem is hard, so let us go through this problem description very quickly. We have been given an array of integers nums, and there is a sliding window of size k, which is moving from the very left of the array to the very right. You can only see k numbers in the window, which should be obvious. Each time the sliding window moves right by one position, we have to return the maximum sliding window, as in, uh, okay, so please go through these constraints and this example. Now, I hope you have went through this. So let me jump quickly to the dashboard and we'll try to investigate and try to solve this problem. So we have been given this array nums and we have been given k, which is equivalent to the window size, okay? So the problem states that this window, it is a fixed size, and at each iteration it is moving by one, or it is shifting by one to the right, okay, something like this. And for each window, before it makes a shift, we have to determine the maximum element in that window, like this, and we have to capture all those elements, and we have to store somewhere, and we have to return that as a list, okay? So suppose if the window shifts n times, so we need to return n elements, which will be representative of every maximum element within every single window before they made a shift, okay? So what will be the brute force approach for this problem? The brute force approach will be every time we have a window, we compute the maximum element in that window and store that in our result array. Then we make a shift. We again try to compute the maximum element in the new window, and then again try to fit that result into the result array. And then again, when the window moves one more to the right, we do the same thing. So as you see, it is a very repetitive task because for each window, we have to compute or scan the entire window to find the maximum element, and we have to store that maximum element in our result array. Something that is not very efficient, not at all efficient to be honest. So this will be something of quadratic time complexity, something that we cannot offer, something that we cannot afford. And so we need to take a look at something much more optimal. So in this problem, as this problem states that we need a sliding window, okay? So we will try to solve this problem from the perspective of sliding window, which should be lesser than quadratic and will revolve around linear time complexity, okay? Before I begin this problem, I'll be using two things. First, an answer array, which will store the answer, and I'll have a DQ. Okay, so what is DQ? I hope you're aware of Q, right? Q is a data structure, correct? Similarly, DQ is a data structure with double AND, where an element can be operated either or on both of those ANDs instead of Q, where in Q we just operate on a single AND, correct? So in DQ we will operate on both of these ANDs, and for convenience of this problem, I'll be using a DQ data structure and an answer data structure, okay? An answer array, which is the data structure, right? So let me tell you how this problem will unfold, the solution for this problem, and we'll try to investigate and answer it, okay, as we proceed. So first of all, we will have two pointers, left and right. Why? Because this is a window case, correct? In window, we need two pointer, left and right, where the window increases more often than not towards the right part using the right pointer, and the left part moves, left pointer moves only when we violate a condition or only when we have to reach to a certain state. Only then we move the left pointer. Otherwise, it is right, which moves perpetually. Okay. Now, at the first stage, what we'll do, we will maintain a data structure double queue and an answer array. And we will be dealing with something called as monotonic decreasing DQ. Okay. Now, what is monotonic decreasing DQ? You will understand what it is. First of all, when I'm at R, I will store one. Okay. Now I'll move my right pointer to the next. Okay. What is the length? The length is 2. Is it equivalent to the window length, which is 3? It is not, right? When I encounter an element which is greater than top of the element at Q, I'll pop that element and will place that element on the top. Okay. Then again, I'll move right pointer next. I see it is -1. Do I need to pop 3? No, we do not. Why? Because -1 is not greater than 3. Okay. So we just put -1 as it is. Now, when I'm at this point, at this instance, what do I notice? I notice that my window length is exactly as it is given in the problem, right? So what do? We take the first or the front part of the queue and we add it in the answer. Okay. And what do we do? Before I make an increase to the R, I ask myself, hey, the element that was added from the front of the queue, is it equivalent to the nums of left index, as in where the left pointer is pointing to in the nums array? Is that element equivalent to the q of 0? It is not, correct? So in that case, I can safely move my left pointer by 1 and right pointer will again move by 1. Okay, so this is the new length of the window, correct? What do I notice? I notice, hey, it is -3. So let us add -3 here. And in answer, since this length is equivalent to the length of the window given, we'll again add 3 here. But again, we ask the same thing. Hey, is nums of L, is it equivalent to q of 0? And the answer is yes, it is. So in that case, we'll pop out q of 0 and we will move left pointer by 1. Right pointer will move accordingly. But when we are R, what do we notice? We notice it is 5 and it is greater than the top of the element, which is -3. So we pop -3. And what do we notice again? We notice that 5 is again greater than -1. So we pop out -1. Our queue is empty and we add 5 to the end. Okay. And we get a new window of this size, right? What do we notice? We notice that in this case, the q of 0 will come over here, which is 5. Okay. And we will ask the same question. Hey, is nums of L, which is at this stage, is it equivalent to q of 0, which is this? The answer is no, correct? So I just move my L to this part, okay? R moves to this part, all right? And the R is 3. Is 3 greater than 5? No, it is not. So let us add 3 over here, okay? And then in this case again, we have achieved a new window length, which is this one, from there to there, okay? And in this case, again, the maximum element is q of 0. So we write 5 again over here. And we ask, hey, is nums of L, is it equivalent to 5? And the answer is no, right? Nums of L is 3 and Q of 0 is 5. So we just move L to the right by 1, okay? And R moves by right to the right by 1, okay? What do we encounter here? We encounter 6, okay? Is 6 greater than 3? Yeah, it is. Please pop 3. Is 6 greater than 5? Yes, it is. Please pop 5. Our queue is empty. Add 6. The new window is of length this one. And in that case, maximum element in this case is 6, which is coming from q of 0. We add that. We ask, hey, is nums of L, is it equivalent to q of 0? The answer is no. Again, we move L by 1. R comes to this part, and let me change the color. We ask, hey, is 7 greater than 6? Answer is yes. Please pop 6, add 7, and we check that the length is again 3. We add 7 over here, right? So this is the exact, and we would have, exhausted the entire loop because R would have accessed the array. And this is the exact answer that we need to return. 3, 3, 5, 5, 6, 7. Okay. So this how were we able to accomplish this thing? We were able to accomplish this thing using an idea called as monotonic increasing or decreasing stack. In this case, it was monotonically decreasing because every time we encountered an element which was smaller than the top of the stack, we simply placed that smaller element on the top of the stack. But if we encountered an element which was greater than the element present on the top of the stack, we popped the element out of the stack until and unless that was the maximum element and we just placed it right. So that was all there is to this problem. Now, let me quickly walk you through this code. What do we do? We first of all have a left pointer called as left of 0. We have initialized it to the left window, like the starting window, right? At this point, and R will also be at this point in the start, right? At index 0, we have maintained a result array. It is something which will accompany our final output, and it is something that we return out of the loop, okay? And we maintain a double-ended queue. In Python, you can simply just call it collections deque. and you will get this thing. Okay. And then we have a loop. We have a loop with a separate iterator called as right, which will be the right part of the window, and it will run across the length of the nums, which will be like order of n time complexity. When we are inside a loop, we are asking, hey, do we have some element in the DQ? And if we have, hey, is the current element on the array that we're looking at, is it greater than the top of the DQ? If that is the case, please pop it. What pop it? Please pop the top of the DQ. As long as this current element is greater than every single element in the DQ, we just keep on popping it, okay? And once we have popped it, popped out everything, and when we break out of this while loop, what we do? We append the nums of right element to the DQ, and then we ask a question, hey, is the current length of the window, is it greater than or equivalent to what was given to us? If that is the case, then please append the first element of the queue. There is one thing that I need you to think about. Okay, we'll come to that. Then please append the Q0 of DQ to the result array. And then we ask, hey, upon appending, if nums of left, if that is equivalent to Q of 0, then what do we do? We know that since this is, suppose this is the current state of the window, and in this window there are three elements, and let us suppose that this was the maximum element, okay? And our left pointer is here, and we have appended this element in the result array, okay? And we are asking in this line, hey, if nums of L, is it equivalent to Q of 0? If that is the case, we know for sure that this window is going to move right by 1, correct? So this element will be discarded anyhow, right? So what do we do? How do we tackle that? We tackle that by checking this condition and popping that element from the left, okay? Because we are certain that that element will be discarded as we make a shift, one shift to the right, okay? And then once we are done with all these things within this if condition, if block itself, where we are checking for the window size, we make an increment to the left pointer. And this loop goes on and on and on until we completely traverse and exhaust all the element in the array. And once that is done, we come out and we return the result. Okay. So yeah, the time complexity is order of n. The space complex. By the way, like one thing that you will notice here is that can we have a case where our DQ will have number of elements that will be greater than k? Can we have such a case? And the answer is no. We can never have a case where the number of elements in our DQ will exceed the number of elements that is present in the window. Okay. So in that case, our space complexity will be bounded within order of k. Okay. Because number of elements in the queue, it will always remain bounded within k. Okay. So yeah, that is all there is or there was about this problem. And time complexity is order of n, space complexity is order of k. Let us move to the LeetCode dashboard and we'll try to submit this problem. I have already written the code, so I'll just simply copy and paste it and I will run it. And as you can see, this problem has been submitted and it has been accepted, right? So what are the edge cases that we have to take a look at? One of the edge cases that what if k is greater than the length of the array. But again, I think this is a pretty vague edge case, and this will not be given to us because this makes no sense. The second edge case might be what if the array is empty? Again, that is something also we can, we can tackle easily, right? What if all the elements in the array are identical? What we'll do then? Uh, in that case, we have to ask our interviewer, like what if we have been given duplicate elements and whether one duplicate elements can be considered strictly greater than the other or not, right? So stuff like that, yeah. So that is all there was about this problem. I hope you enjoyed it, and it was the fifth problem for today, which was a hard level problem. I'll follow with a couple of more problems, maybe of medium difficulty, and might sprinkle a hard in there. But yeah, let us see. Thank you for watching. Stay tuned.